Hi, this is the second part of chapter 14, where we are going to talk about phase changes and latent heat. Now, we know that the major um, phases that we know: solid, liquid, and gas. And here, this is a thought experiment that I have, let's say, 2 kilograms of ice at negative 15 degrees Celsius, and then I start warming it up. And, one of the things that we need to know, the ice will not start melting right away because ice cannot melt until it's 0 degrees Celsius. Then the ice is gonna stay ice during this period of time here. All what is gonna happen is I'm gonna uh, actually um, warm it up so that it will reach zero. And therefore here I can calculate the heat by saying it is MCI, stands for ice, times delta T. Now, when it reaches zero here, okay, then now we are going to start having the melting. Okay, and this was negative 15. Okay, and then while it is melting, the temperature is going to stay at zero. And we're going to find that ice and water, they're going to coexist in equilibrium. Now, if I wish to calculate Q, which is the heat needed, now I'm going to use a new equation here, and that equation, it is M times LF. LF called latent heat of a fusion. After that, okay, I have now all is ice, all is liquid, it is just water, and therefore we're gonna have its temperature changing from 0 to 20 to 40 to 60, 80 till it reaches 100. At 100, we're gonna have the boiling starting. Here, if I wish to calculate the amount of heat I need, this is gonna be Q3 MC water times delta T. After that, okay, we are going to have now boiling, where steam and also evaporation is going to occur at all the parts of the liquid. And then I can calculate this by having a new phase change here. Q4 is going to be the mass times LV. LV, it is the latent heat of evaporation. And then finally, I will reach a point where all of it is steam. And then here I can actually have the steam going from 100 to 120, 140. And then Q5 is going to be MC steam times delta T. If I wish to calculate what is really the total energy here used, I need to add Q1 plus Q2 plus Q3, Q4, Q5. Okay, here I'm summarizing all the things that I was talking to you about: how to raise the temperature of ice from negative 15 to 0. This is occurring from A to B. Let's assume I have 1 kilogram. Then a Q1 is going to be M ice times C ice times delta T. And this is how I'm going to calculate that. For BC, it's going to be a plateau, or like a line that is horizontal, no slope. The slope is 0. Here it has a slope. Here it has a 0 slope. And then Q, it is M times LF, and LF, it is the latent heat of fusion. And the amount of heat needed to melt 1 kilogram of the substance, it is called the latent heat. And this is from B to C. C to D, it's another raise of temperature, which is having that slope again. And in order to calculate Q3, we're going to say MCW, which stands for water times delta T. From D to E is going to be another phase change, horizontal. And we are going to change from liquid to gas. The temperature is going to stay the same, it will not change, and Q4 can be calculated as M times LV. LV, it is the latent heat of evaporation. And then Q5, it will be MC steam times delta T. If I wish to calculate the whole thing, is going to be Q equals Q1 plus Q2 plus Q3 plus Q4 plus Q5. Now, here I have a question. A bag containing zero ice is much more effective in absorbing energy than one containing the same amount of zero water. How much heat transfer is necessary to raise the temperature of 0.8 kilogram of water from 0 to 30, and how much heat transfer is required to first melt the 0.8 kilograms of ice and then raise its temperature? Explain how your answer supports the contention that the ice is more effective. Now I will calculate Q here. What is really the amount of heat that used to raise the temperature of 0.8 from 0 to 30? Then it is MC delta T 0.8 times, this is C for liquid water, 4186 times 30 degrees, and that is going to be 110 to the 5 joules. And for B, I'm going to add in addition to, because here I need first to melt and then to raise the temperature. For melting, this is what I need, which is mass times LF plus MC delta T that was calculated here. And therefore, you're going to find that this is 3.68 10 to the 5. Now then ice, it is like I can explain that ice is much more effective because I need first to melt it, and then the ice is going to take that heat from the environment, and then it's going to take another amount of heat to raise the temperature to 30. Another question here. How much heat transfer is necessary to raise the temperature of a 0.2 kilogram piece of ice from negative 20 to 130, including the energy needed for phase changes? And how much time is required for each stage, assuming a constant 20 kilojoule per second rate of heat transfer? Make a graph of temperature versus time for this process. Here, it's the same steps that I was talking to you about. I have here the mass is 0.2 kilogram ice. Initially, it is at negative 20. The steam, I will change it to steam at 130. Now, first one, Q1, the heat needed to warm ice to 0, and that is Q1 equals MC ice times delta T. And this is in kilojoules. A Q2, it is the heat needed to melt the ice, and it's going to be the 0.2 kilograms times 334 kilojoule per kilogram. And then here also I have the answer in kilojoules. A Q3, it is the heat required to warm 0 degrees Celsius of water to 100 degrees Celsius. And that is Q3, it is MI, mass of the ice, times CW times delta T. And this is going to result in 83.73 kilojoules. Number 4, it is the heat required to evaporate the water at 100 degrees Celsius. And then I'm going to multiply by the latent heat of evaporation. Number 5, it is the heat required to warm 100 degree vapor to 130. And then I'm going to add all of them. All right. I'm going to stop here. I'm going to have another video. Thank you.